Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Especially good morning, Dr. Asawer. Welcome to Universitas Erlangga, even only virtual. The Honorable Lecturer of Algebra Research Group, and also the Honorable participant of this lecture. First of all, let me introduce myself. I am Sahida, the moderator of today's lecture. I'm very pleased to see you here and welcome all of you to this lecture.
Thank you, Zahida.
Our speaker today is Dr. Asawer Hamdi from University of Baghdad. Her research area is in semigroup theory, especially idempotents in semigroup theory. Before the lecture begins, let me inform you how the lecture will be going on. First, Dr. Asawer will be invited to present the materials about 60 minutes. After that, there will be question and answer session about 20 minutes. Participant could type the question on chat box or use raise hand reaction. Now, let me to welcome Dr. Asawer to deliver the presentation. Dr. Asawer, the time is yours.
Hi, Assalamu alaikum, everybody. First, let me introduce myself. I am Asawer Hamdi. I am a lecturer at University of Baghdad. I got my PhD from the University of York. My field is in algebra, especially in semigroup theory. I am very pleased and very thankful to have this lecture from the University of Erlangen. This is a good opportunity for me, and I hope me and you can have a benefit from my lecture. So my lecture is on idempotent in semigroup theory, and can I now close the camera first, please?
Yeah, sure.
Yeah, thank you. Okay. So the outline of my lecture will be have basic definitions for semigroup, and then subsemigroup and ideals, idempotents, and the idempotents in the special semigroup, the full transformation semigroup, Tx and Tn. And then I will explain what the meaning of free left as act, and then what is the meaning of product semigroup, series Tn, and what is the idempotent in the product. Okay, now, first, the basic definitions will be on semigroup. Semigroup is a pair with a non-empty set S with an operation. This operation have to be associative binary operation, which means this function is from the Cartesian product S cross X to S with, if we have a pair of AB go to A star B, and we can see here for all A, B, and C in S, we have, this is associative binary operation here, A, B, C, and equal to A, B, C here. This is what the meaning of the associative. This semigroup, the second definition, a monoid is a semigroup with identity. So this means if the semigroup have one, this one means not exactly one, it means the identity of the set. Such that if this identity, if we are take it or multiply it with all elements in M, will give me A. 1 with A equal A, or A with 1 equal A. And we can notice here the identity of monoid have to be unique. Okay. Now, everybody know what is the meaning of a group in the group theory. So a group is a monoid, such that for all elements in G or in a group G, there exists an element B in G with AB equal 1 and BA equal 1. This B here meaning the inverse of A. We know all of us that in the group theory, group have to have an identity and inverse element. So B here, it is an inverse element for A. Group are monoids and monoids are semigroups. This means all group have to be monoid because it have an identity, and all monoids are semigroup, but the converse is not true. So it is not necessary all semigroups have to be group. So we can explain this by an example. The one element or trivial group, a set of have one element, which is the E here, with multiplication. So the operation here, we have a multiplication, is also called the trivial semigroup or trivial monoid. A ring is a semigroup under multiplication. If a ring has an identity, then this semigroup is a monoid. So the ring is a semigroup, but if it has an identity, this semigroup will be a monoid. The natural numbers is a monoid under the multiplication. The natural numbers is a semigroup under addition, and the natural numbers union, the 0, is a monoid under the multiplication and the addition. So now, the most important example in semigroup theory is this. Let X be a non-empty set, and let Tx is the set of all functions that take X to itself. This set is called the full transformation semigroup, and the operation with this set have to be the operation of composition. And if X here, this X, if it is finite, so this means this set have to be from 1 to n. So we will write Tn for Tx. We often, in semigroup theory or on all papers, on all books, speak about full transformation semigroup. We often write the operation of composition as a multiplication, which means if we have alpha and beta in Tx, then we can write the multiplication as this. And I want to mention here, in all semigroup theory, the operation have to be from left to right, not from right to left. So we say here, x alpha beta, this means x alpha beta, like this as a multiplication, and this mean is alpha x first, and then we take beta for it, for all x in x. The full transformation semigroup has an identity. This identity called the identity transformation, which I also take the set X to itself. And for any alpha in Tx, the multiplication alpha with Ix give me alpha Ix as well, and have to give me alpha. So this is an identity in the full transformation semigroup. So this semigroup with identity have to be a monoid. Hence, Tx with the operation of composition is a monoid. Now, I will explain what the meaning of subsemigroups and ideals in semigroup theory. Let S be a semigroup And here T is a non-empty subset of S. Then T is a subsemi group of S if for any A and B, or for any two elements in this subset, implies the multiplication of them have to be also in T. Now, if S is a monoid, if S has an identity, then this T is a submonoid of S, with condition that if T have to be a semigroup first, subsemigroup first, and the one have to be in T. This one is the one of S. So the subsemigroup is a monoid when this T have to be first a subsemigroup, and the one here have to be in T. Now, what is the ideals in semigroup theory? So a non-empty subsemigroup T of a semigroup S is a left or right ideal of S if and only if. This is the definition of the left. If we can multiply this subsemigroup of S from the left, and this multiplication in T, then we call this T is a left ideal. Or if we can multiply this subsemigroup with S from right, then we have to tell this subsemigroup is an ideal or a right ideal. And T is a two-sided ideal if and only if it is a left and right ideal together. Notice that if S is a monoid with identity, then an ideal of S is equal to S, if and only if the identity is in T. Okay, so the examples for subsemigroups and ideal is here. The natural numbers with multiplication is a subsemigroup of the integers with the same operation. The set of all constant element in the full transformation semigroup is a subsemigroup of the full transformation. And this is the reason we can, it is easy to prove it, Cx, Yx, it is a Cx because this is a constant. So when we multiply Cx, this is mean the map in Tx has X only in the image. If we are multiply it with the map have Y only in the image, will give me X only by composition. Composition of maps in Tx will give me Cx. So we can see here the multiplication of two elements in Tx give me an element of Tx. So this set have to be subsemigroup. And if we have Y is a subset in a set X, then we have the set of elements in Tx such that the image is a subset of Y is a left ideal of Tx. This is also easy to prove. And for any element, for any integer element, then S to power n is the set of all elements here from 1 to n is an ideal of S. And if S is a monoid, then Sn is S. Why? Because here we can see here S have to be S element from here. So if I put from 1 to 1 n minus 1 times, you can see here S will be equal to S. So Sn here is S for any S in S. So these are examples for a subsemigroups and an ideal. And they are very easy. Now, This is here, this definition, I will explain the meaning of idempotent, which is the main of my lecture. An idempotent element, E in S, we call it sometimes E or, or any element, but always we call it E because it is for us as in a semigroup, we can understand it. This means, oh, okay, this is an identity, an idempotent, sorry. So an idempotent is an element E in S such that E is E squared. We put the set of all idempotents elements like this, ES, which is all the set, all the element in S such that E is E squared. If S is a monoid, it's clear that the identity will belong to this set because 1 equal to 1 squared. Now, this is a fact. Any finite semigroup contains an idempotent. So when we can see a finite semigroup in a semigroup theory, and we have to say this set have to have an idempotent. So this is fact, and very important fact. Now, what is the idempotent in the full transformation semigroup? First, let me explain if we have element in the full transformation semigroup, what can we describe it first, and then what is the idempotent element in Tx? If alpha is an element in full transformation semigroup, then alpha can be written as this. This is the image of alpha, the domain of alpha, because I think I have to write here Tn. I think this is a mistake, a typo mistake. I have to write here Tn because my element is from 1 to n. So the domain here from 1 to n and the image, this is the image of all elements, alpha 1, alpha 2 to alpha n. I want to mention that not every element in the full transformation monoid is 1-to-1. We can have, for example, 1 take me to 1 and 2 take me to 1. So this is not 1-to-1. So from this fact, not every element in the Fourier transformation monoid is 1-to-1. From this fact, the second row, this second row, in alpha above is not a permutation for the first row. The full transformation monoid, this lemma, give me how many elements in the full transformation monoid. The full transformation monoid Tn contains n to the n elements. So if I have, for example, T3, so 3 to power 3 have to be, T3 have to have 27 elements. We define the rank of an element alpha in Tx to be the cardinality of image alpha. What meaning of the cardinality? Cardinality is the meaning, is the number of elements in the image. How many elements here? This gives me the cardinality of image alpha. And in the most time, we call it rank alpha. Image alpha, what is image alpha? Image alpha is all elements alpha x, such that x in x. So the element here. Now, in order to know what is the idempotent element in Tx, first let me explain the meaning of the restriction map. If we have a map alpha from U to V, such that we have a set Z is a subset from U, then the restriction of alpha of the set to the set Z is a map. This means the restriction from Z to V. And this take all the elements of Z to alpha Z. Sometimes we treat the restriction of the set Z as a map with a domain Z and the codomain alpha Z. This is help us to write the elements of alpha X actually, because in flow transformation semigroup, the elements depend on the image. So we all the time need the restriction map. Now, this lemma give me to understand how to find the elements in the flow transformation semigroup. An element in a flow transformation semigroup is an idempotent if and only if the restriction of this element on the image is the identity transformation semigroup on the image. And this is actually easy to prove, but I will explain it now, how this lemma work. Let me explain it here. If we have by the idempotent element in the flow transformation semigroup, we can list all the idempotents in T3. T3 we spoke before that because it's T3, so the element of T3 have to be 3 to power 3. So in T3 we have 27 elements. Now, how can I know by using this lemma? How can I know what is the idempotent without test every element that alpha is alpha square, just by using the previous lemma? Let me explain how. Now we start with elements in T3 have one element in the image. One element in the image. So this is, we have 3 elements in T3 have one element in the image. This is C1, C2, and C3. We call it C1 because have 1 in the image, 1, 1, 1, and C2 here, 2, 2, 2, and C3. We can see here, since the image is 1, so what I have to have, 1, the image of 1 have to be 1. And all the rest of and the 2 have to be 1, 3 have to be 1. But this is the most important, 1 have to be 1. Look at here, this image has 2. We have 2 in the image. Just one element is 2. So 2 have go to 2. And here 3 have go to 3. I think here is not clear, but if we have 2 elements in the image, must be clear. Let me explain how. Look at here. We have 2 elements in the image, is 2 and 3. So what we have to have? We have 2 go to 2 and 3 go to 3. So 1 have to go either to 2 or either to 3. So these elements are idempotents. Now, this element, what elements in the image? 1 and 3. So 1 go to 1, 3 go to 3. So what about 2? Have go to either 1 or 3. So these are idempotent. And the same thing for this. My image is 1 and 2. So I have 1 go to 2, 1 go to 1, and 2 go to 2. So 3 have go to either to 1 or 2. all these elements are idempotent with the previous, by using previous lemma. Now, if we have 3 elements in the image, so this is the identity transformation actually. So my elements in the image have to be 1, 2, 3. So 1 have go to 1, 2 go to 2, and 3 go to 3. So this is an idempotent. Now, from this and from the previous lemma, we know how to find the how we can know these elements are idempotent. Now, if I want to count this, how many idempotent elements in the full transformation semigroup? This formula gives me the number of idempotent elements in the full transformation semigroup. So this is a summation, go from k to 1, k equal 1 to n, and n choose k, and k to n power n minus k. K here, it's image alpha, is the number of image alpha, or is the rank of alpha. So this formula gives me the number of idempotent elements in the full transformation semigroup. Now, in order to explain the meaning of free products in the coming slides, first I need to explain the meaning of free left S-act in semigroup. A non-empty set A is a left S-act if there exists a map from S, it is the Cartesian product of S cross A to A. So left, because S here is from the left. So this is the map here, such that for all A in A and ST in S, will give me this STA is STA and 1A is A. So this is the condition for the left S-act. Now, if we have let A and B to left S-act, so a mapping alpha from A to B is called a homomorphism of left S-act, or we can say it just an S-morphism. If this alpha SA equal S A alpha for all A in A and S in S. Now, the free left S-act, what is the construction of the free left S-act? Free left S-act, we will, in the most time, we will call it like this, FXS, which is the disjoint union of all the set of the form Sx, where this set is all the element of S small, X small, where this X in our X here, and S in S. In the case if X is a finite element, we usually write FNS for FXS. And if it's trivial sets, we say X is X. So this set have to be Sx, and it's clear that it is isomorphic to S. Where S is regarded as a left ideal of S. So we will use this definition most at most in our proof in semigroup theory. We have to know what the meaning of FXS have to be the disjoint union here. Now, this is here, this is left S act. This is just left S act. So if I want to say this set have to be free left S act, what I have to, what is condition? Give me this set to be free left S act. So this is very important definition, and this is a fact actually. If we have a set X here, this is a basis. Let X be a non-empty set. This is a basis of Fsx, and let Fxs is a free. Just a moment. We have X here be a non-empty set, and we have left S act here. So this is free. This is a free left S act if there is a map alpha from X to Fx, if there is a map here between those. And for every S act A, this is have to be S act. So this is S act, left S act, and this is have to be S act. For every S act A and every map, phi from X to A, there exists a unique morphism psi from Fxs to A, such that this diagram have to be commutes. This means alpha circle psi have to give me phi. So in this diagram, if this diagram is commute, this set we call it a free left S act. Now we will speak about the set called the endomorphism monoid of a free left S act. Now we have a free left S act, and we will speak about the set we will call it the endomorphism monoid of free left S act. We will take an element alpha in this set. Actually, this set is a set of maps. Take the free left S act to itself. Now, if alpha is belong to the endomorphism monoid, and if we have I from 1 to n, then this map defined as follows: alpha xi is omega I alpha xi alpha bar, where this alpha bar in the follow transformation semigroup Tn. And this omega here from 1 to n is belong to Sn. And as this alpha is in endomorphism monoid, so it is an S morphism. So from the definition of an S morphism, alpha Sxi will give me this, S will be out, and will equal to this alpha Xi is here, we put it here. So this, the definition of elements belong to the set, belong to the endomorphism monoid of a free left S act. From this definition, we will define
Salam. Hey, thank you.
Now, from the previous definition, we will define a new semigroup. We will call it arithmetic semigroup. We define the arithmetic multiplication. This is a direct product of Sn by Tn by putting these elements. Actually, this one is element and this one is element. Multiplication those will give me this. This is from the element S1 to Sn, new here. This new is belong to Tn, and those are in Sn. So Sn cross Tn is this, and another element T1 to Tn new. The multiplication between them will give me this. If you can look here, this element T1 new, this element, the multiplication will depend on the first one, S1 T1 new to Sn Tn new. And here, this have to be the multiplication between new and new. So we will depend on this multiplication in the Riemann product. So every Riemann product in semigroup theory, this we have to have this multiplication. So under this multiplication, the direct product here becomes a monoid with identity, this one. So the identity from 1 to 1, but here the element have to be the identity transformation semigroup. And it is denoted by this multiplication, this product with this multiplication will give me a Riemann product. We will call it or denote it like this, S Riemann Tn, S Riemann Tn. So this is fact actually. This lemma is fact. All the endomorphism monoid for free left S act is isomorphic to the Riemann product S Riemann Tn. This is fact actually. So if here is a semigroup, but if we put here, for example, a group, so the endomorphism monoid for free G left for free left G act, so we have to put here G. So well, if this G, this is will be isomorphic to G Riemann Tn. Now, how we can find, like we in the previous slides explain the rules to find the elements in the full transformation semigroup, and we have a formula to find how many elements in there. But now we want to know how we can find what is our rule to find the idempotent elements in the Riemann product S Riemann Tn, and what is the formula we can use to know how many elements in there. So let us explain the following lemma. Let A be an element in a Riemann product. Then A is an idempotent. Idempotent is mean A equal to A square. Then A is an idempotent if and only if this tau is an idempotent and Si equal to Si Ti tau for all I is from 1 to n. How we can prove this is too easy actually. We have element A here. What we said A is an idempotent, so A square have to be like this. This when we multiply A by using the previous multiplication in the Riemann product. So this give me the previous this one by using this multiplication. So this is A multiply A will give me this. So that this A is idempotent, so that A is A square if and only if Si give from is come from here, and this is come from here, which is this one. So Si is Si tau. So this, I think it's clear from here for all I from 1 to n. And look at here, tau is we have tau have to be idempotent because from this equality, tau will be equal to tau squared. So this is our rule to know the idempotents in the full transformation semigroup. And if A is an element in the Riemann product, we define the rank of A to be the rank of alpha. So if A is this element, so the rank of all this A has equal to the rank of alpha. Rank of alpha is the number of image in alpha, actually. Now, if I want to find the number of elements in S raised to n, actually, in order to understand how to find the number of idempotent element in S raised to n, first we will speak about special case if we have here a group. This is help us to understand the formula, because the formula to finding the idempotent in semigroup is very difficult actually, and it take from me about 6 months to find it when I was in York, but it is easy now. Now let us explain the number, how we can find the number of idempotent element in G raised to n. So we have here a corollary. Let G be a group and A is an element in the Riemann product G raised to n. Then A is an idempotent if and only if this mu is mu squares, mean mu is idempotent, and G sub J equal to 1, where J is in the image. Actually, to finding the number of idempotent in G raised to n is too easy because G has an inverse. So by using the multiplication before, we can use the inverse condition for group, and from this fact, we can have this one. What this mean? This mean that if we have, like an example before, an image, for example, alpha, our image in alpha, for example, is 1, 2. So what I have to have here, G1 have to be 1, G2 have to be 1. If our image is, for example, 2, 3 in alpha, so G2 have to be 1 and G3 have to be 1. And the example is too long, so it is meaningless to put it here, but it is actually too easy. Now, this is the rule, how to find the number, how to find the elements, the idempotent elements in Riemann product. But what is the formula to find these elements in the G raised to n actually? The formula is this, is the summation of n choose k, where k to the power n minus k, and this is the number of element in G to n minus k. If we can focus here about this, actually this is the number of idempotent elements in the full transformation semigroup. Multiply it with the number of element in G power n minus k. So this is the formula, give me the number of elements of idempotent elements in raised G and G raised to n actually. Now, what is the most important thing in this lecture is how to find the number of idempotent in a Riemann product S raised to n. Here S is a finite monoid, So this is a special case because here we have G, a group, and the group is a semigroup actually, but it's a special case. So if you have general case, general case, but S here have to be a finite monoid. It is, I think, so difficult to find a number of idempotent in S where S is any monoid, or a monoid without saying finite. So, and we say finite here because there is a lemma before said that every finite semigroup has a monoid, has an idempotent, sorry. Now, let S be a finite monoid and let F be an element in the idempotent set of S, and put PF be the number of elements in S such that this F multiplying from right with S give me S. If we multiply it from right with S, give me S. This is idempotent, but this is any element. Now define rho here be equal to PE, which is this, where E is an element, an idempotent element in S. For all L in P or in rho, let ML be the number of idempotent element in S such that this PE equal to L. Actually, this is very difficult explanation, but this is the conclusion actually. So the number of idempotent elements in the S raised Tn, where S is a finite semigroup equal to this formula. Actually, in our proof, to prove this, we use the multinomial theorem to find the number of idempotents in S raised Tn, and from the multinomial theorem, we have this. And actually here, this is the general case. The special case is the previous formula. If we have a group, so if we have a group instead of S, so this formula will give me the formula before is this one, And this is the end of my lecture. I hope you have a benefit from it. And thank you very much. Any question?
Okay, thank you very much, Dr. Asawer, for giving us such informative and interesting presentation.
Thank you.
Okay, dear our participant, now come to the question and answer session. Let me take a look at chat box. Is there any question? You may type your question on the chat box or raise your hand using direction on the Zoom. This topic quite new for us here, Doctor, because we haven't discussed about this topic yet. We just discuss in abstract algebra only in group.
Okay.
Or maybe while we wait the question, I have a question regarding this topic.
Okay.
Is there any suggestion for the future research about this topic? Maybe our student can learn about this or use the topic for final project.
Well, actually, this topic is where I studied this topic degree. I was attended this with MS student, and now hi, can you hear me?
Yes, right now is quite
Okay.
good.
Yeah, okay, sorry. And now, actually, in my country, I am teaching this in postgraduate student, yeah, in MSc. So for undergraduate, I think it is too difficult for them. They have to study algebra or ring theory first in order to they are ready to understand the semigroup theory, actually. But they can just have the basic definitions for semigroup, not go too far with it, actually. Just this, and this is all. I think it is very useful to know what is semigroup. But it is too early for them if they are undergraduate, actually. This is.
Or maybe you can give us some paper or article, the latest maybe.
Okay, yes, actually I have presentation for research products.
Okay.
I have a paper and presentation for GREAD Sync-In. Yes, a paper, and my thesis is combinatorial product for S3STM. This is, and there are lots of papers for my supervisor, for example, independence algebra and semigroup theory, and my supervisor, she is Victoria Gold. Anyone can search on it, on her. She's very famous, and they can have a very useful papers from her. But for me, now I am searching on finding the number of ideals in the partial transformation semigroup and the number of ideals in the full transformation semigroups. Now I'm searching on it. I'm working on these papers. So yeah, lots of papers are interesting in my field, and they can search on Jim East. He is very famous Australian professor in Sydney, and they can actually I cannot remember what his papers maybe. Yes, presentation in for singular semigroup as Sync-In, and they can search on Howie, John Howie is very famous, and on John Fountain, their paper independence algebra, and papers on free left as act, and etc. and etc. Yeah.
Okay, thank you for the answer. We have 2 questions here on chat box. Let me read it. From Nindi Trikusuma. Please, on slide 21, please give us an example to count the number of idempotent, if I'm not mistaken. And the second one, is it possible for semigroup has a group subset?
For the first one, do you mean how I can find the number of idempotent in which set? In any set, or do you mean in Riemann product?
The last one.
Then the Riemann product, an example? Actually, I just explained it now, but there is an example actually, but it is to finding the number of idempotent in GREAD. And I can, if it is actually very difficult to explain it here. If they wanted, I can send the PDF file for the example for finding the number of idempotent for GRESTN. Actually, it's very easy to find. It depends on these elements here. Let me explain just in simple way. It's something like these elements, and if we have, for example, one element in the image, so my image here is 1. So by the lemma we explain, so G have to be 1, and here in the image we have 2 in the image. One element is 2, so G2 have to be 2, and here we have 3, so G3 have to be 3. But for 2 elements in the image, for example, 2, 3, so G2 have to be 1, and G3 have to be 1. But G1 is take any elements in the group. So it is it's about 46 elements actually, idempotents elements in GRESTN, and it's too long to explain it here. If they are interesting, I can send the PDF file for the example actually, but I didn't put it here because it's too long. Yes, what about the second one? I cannot understand it very clear. What is the second example, please? Question, please.
Maybe the question, the meaning is it possible for semigroup has subsemi group? Maybe.
Subsemi group from what? From GRESTN or SRESTN? From which set? Any semigroup, I can find a subsemi group. By
for any semigroup, we can find.
We can find a subsemi group. Yeah. If it is satisfied the condition of a subsemi group, that is, if any 2 elements, the multiplication of any 2 elements here have to be in this set. So the any elements in T, the multiplication between them, if it is in T, so T will be a subsemi group. So if this condition is satisfied, I can't find the subsemi group in sets if this condition is held.
Which means if we have any kind of structure of set, we can find any the subset of the structure.
Yeah.
Oh, there is another. I think he asked about that. Can it be the subsemi group is also a group?
The subsemi group is also a group.
The question that Dimas asked, I think he asked about if some semigroup has a subsemigroup. Can it be that the subsemigroup is a group?
Yes, sure. Yeah, sure. So from here, so you can see here, this is N with multiplication, a subsemi group with Z with multiplication, natural numbers and integer numbers. But this one is a group. So it is a group and it is at the same time is a subsemi group. So this is a question.
Okay, how Ahmad Nadimas? Did Dr. Asawer answer your question?
Yeah.
You can unmute your microphone. Okay, it's clear. He typed in Indonesian. Okay, for Nindi, later Dr. Asawer will give us the file for the example.
Yeah, okay. When I can send it, I send it to you, to your email.
Yeah, sure.
Okay.
Okay, is there another question? Okay, we have question from Ahmad Sharif. Could you explain the lemma in the early slide? How can it be claimed that semigroup has idempotent?
Can you explain again, please? Because the internet is
Okay. Could you explain the lemma in the early slide? How can it be claimed that semigroup has idempotent? I mean, maybe has an idempotent element. Yeah.
I mean, finance, this one?
Which one, Sharif?
Which
Before
slide?
the previous one.
This one? A finite semigroup. Any
Yeah.
finite semigroup contains an idempotent. This is a fact. Any finite semigroup, if you have a finite semigroup, so this means this semigroup have to have an idempotent. So this is a fact. So when you have, for example, a problem, or you have a paper, and you have a finite set, so you have to know this have to be have to have an idempotent, and you can work on it. So
Sorry, yeah. Doctor, we cannot hear your voice clearly.
My voice?
Yeah.
My voice?
Yeah, right now it's okay.
For a moment, just
yeah, no problem. Please, you can.
Okay, because the internet is not good. Actually, any semigroup, any finite semigroup, if anybody work, for example, in a finite semigroup, and he claim in his work this is a finite, so and he want to comment, or he wants, sometimes we want to know if this contain an idempotent or no. So this lemma just give him a fact that any finite semigroup is an idempotent. So don't go and find papers, or take a moment to think. Just understand that your set is a finite, so your set have to have an idempotent. But it depends on your set. What is the rule of your idempotent? If your set is a simple semigroup, which condition is a simple, or your semigroup is a arithmetic semigroup, you have to have the formula, which I explained before. So, but your condition have to be finite semigroup. So my work is on finite semigroup, and from this fact, I can find the number of idempotent in the arithmetic, where S is a finite semigroup. I don't know if it's clear.
How, Sarif?
Is my voice clear, or my
yes.
explanation is clear?
Yes, your voice is clear.
Okay.
How, Sarif? Okay, thanks. It's clear.
Okay.
Any question? Okay, if there is no question anymore, Alhamdulillah, we finally come to the end of this lecture. And before I close this lecture, let's take some picture together for documentation. Please turn your camera on and give us your best pose.
Okay.
Okay. Please, Doctor, you may stop share your screen.
Okay.
Okay, on my laptop there are 5 slides, 5 pages. So I need to take 5 times. Okay, for the first slide, please, Doctor, you can turn your camera on.
On.
Yeah, okay. Just a minute. Okay, 3, 2, 1, and say cheers. Okay, the second one. 1, 2, 3. Third one. 1, 2, 3. The fourth one. 1, 2, 3. And the last one. 1, 2, 3. Okay. Thank you very much. And lastly, I would like to thank again to the presenter for sharing her knowledge, and also to all the participants for the very active participation. Let's give the applause for the speaker and for you all. And as moderator, I apologize for any mistake that happened during the lecture. And thank you, and see you on next lecture or seminar. Wassalamualaikum warahmatullahi wabarakatuh. Bye. Thank you, Doctor. You may leave Zoom now.
Okay, thank you.